So let me. Today there is a speaker from SISSA, RPG speaker from SISSA, Gabriele Codega. And today's talk is entitled Machine Learning Based Quadratic Closures for Non-Intrusive Reducible. So the stage is yours.
Okay, thank you. Thanks everybody for being here, and thanks for having me in this seminar. I'm sorry, you might have already heard this talk because I already gave almost the same exact one. So if you already know what I'm going to talk about, I'm sorry. So with respect to last time, I've decided to change things up a little bit. And well, first of all, let me say that this is a joint work, as you can see, with Anna Vagnas, Nicola Demon, and Luigi Rocha. And we're going to talk about reduced order models and some shenanigans regarding ROMs. Now, actually, let's never done this before, but if you have questions on anything, please feel free to interrupt during the presentation. So maybe we can do something more interactive and less boring. And I want to start by showing you this. No, I don't want to start. Yes, showing you this picture. This is supposed to be a diagram that summarizes the methodology, right? And when I made this, I was very proud of myself because in my head it was very clear. The whole procedure was very well summarized, but then later I realized that if you have no idea of what I'm going to talk about, maybe this doesn't really make any sense, right? So I fear that during this talk we would our goal would be to make sense of this diagram right here, right? So as we do, we start by giving some context to this work. And first thing I want to show you is a picture. This is San Pietro in Rome. And you might wonder why I'm showing you this picture. And so apart from being a magnificent piece of architecture and Italian pride, I would say, this also took almost 100 years to complete. So a total of 7 popes went by without ever seeing the cathedral complete. So why do we care? Because, well, most of us work in fluid dynamics. So you might know that in fluid dynamics, we have some specific classes of problems that would realistically take order of 100 years or even more to solve with current technology, say. So sometimes, actually, unlucky for us, many of the arguably most interesting simulations one would like to make are those that you start now on a computer on a very high-end cluster, and then you have to wait around for 100 years for it to complete. So that's something we don't really want to do. We don't want to wait around that long. Okay. So we came up over the course of the past few decades with methodologies to speed things up. So you could think of, instead of waiting around 100 years to build the old cathedral, just replace it with a very accurate approximation, right? In this picture, this one on the right is the approximation. This is the real thing. And the idea is basically the same. You can find different methodologies that are more tractable, easier to work with, faster, that still convey all the information you want to take out of your very expensive simulation, right? And this naturally brings us on to the next chapter, which is ROMs. I think most of you are already familiar with reduced order models, but just for the sake of completeness and sake of clarity, let me spend a few words on ROMs. First of all, ROMs is an acronym, stands for reduced order model. And reduced order models are to full order models as the sketch you're just seeing is to the real thing, to the real cathedral, right? So in general, you could say that a reduced order model is a compact, compressed representation of some other large, expensive mathematical model. Typically, you build, I say typically because now you also have some other exotic stuff, but typically ROMs are built with data. So you have either data from prior simulations or experiments or whatever, and you find clever ways to combine those data into some small compact model. For instance, you could think of the full order high fidelity model as being an OpenFOAM solver. OpenFOAM is very popular in the CFD community. It's a finite volume solver, right? Finite volume code. There's many solvers in OpenFOAM, but say you want to simulate a specific flow, and there is a solver in OpenFOAM that does that for you. You can either use that and wait around 100 years, or maybe you can run that solver through WinRAR and get a zip version of your solver, right? So that's not quite what happens, but the idea is that your zip file is easier to carry around, is more compact. You can work with that very quickly, but it still retains all the original information that you're looking for, right? And since ROMs have been around for a while, you can imagine that they come in many different flavors. You have intrusive ROMs, non-intrusive ROMs, equation-based, data-driven. You've got linear, non-linear, machine learning stuff. You've got autoencoders, latent dynamics, you name it. And of course, we won't focus on all of these. We will we will focus on non-intrusive projection-based ROMs. And to explain what those are, I'm going to show you the classical picture you've already seen a million times, probably. This is the typical, say, diagram to represent non-intrusive, so data-driven, projection-based reduced order models. Let me guide you through the picture. Basically, as I told you, ROMs are built on data. So we start with some data. Those data are these blue points right here. The data, in this case, you can think of it as snapshots from a high fidelity simulation. So you run your OpenFOAM solver for different values of some physical parameters. Say you change Reynolds number and you run different simulations. You gather snapshots, and each snapshot, you can look at that either as an image or at a more, say, abstract level. It's ultimately just a very, very big vector that represents the value of some field at a certain large number of physical locations in your domain, right? So you have a discretized domain with 1 million points. In each point, you have a value for the velocity field. And if you think of that, these vectors, basically, we assume that these very high dimensional points lie on some high dimensional manifold, which is this blue kind of sheet of paper, whatever, right? And the expensive thing is to work on this blue manifold right here. So since it's so high dimensional, it's difficult to work with that. And we want to find a clever way to represent that with something which is more compact and more tractable. In practice, what we do here is we find a projection map, a linear projection map from the high dimensional space to a low dimensional linear space. This procedure is called proper orthogonal decomposition, and ultimately allows you to approximate a high dimensional solution as the linear combination of a number of modes that you find through this projection procedure. Basically, you just do a singular value decomposition of your data, okay? And then instead of trying to find the value of your field at each node in your high dimensional mesh, you can simply look for the coefficients with respect to the POD modes. So basically, you're looking for points in here. Whenever you have a new parameter, mu star, a new value for the Reynolds number, you want the full solution. Instead of looking for the full solution directly here, you look for coefficients in this space, which is small. And once you have that, you can map it back and hopefully land somewhere near the actual solution, right? And I say hopefully because in practice, you are never exactly on the actual solution because of several reasons. One of them being that some problems are inherently non-linear. So as I told you, this reduction procedure is linear. You do a linear projection from some non-linear space onto a linear subspace, but Navier-Stokes equations are non-linear. The dynamics might be convection dominated. So in practice, when you go back, there's going to be some discrepancy between your deconstructed full order solution and your approximation, right? And not only that, but also in practice, as you can see, we do a summation over a finite number of modes. R is some integer that you fix a priori. Typically, you want that to be as small as possible, 5, 10, 100 even, but in practice, it's going to be a small number compared to the full dimension, right? And naturally, if you have to pick a finite R, then you're going to have to truncate your sum at some point. Even if, for instance, in principle, you could build a summation with 1 million modes, in practice, you want to work with 10. So the other 900,000, whatever, they are just thrown away, right? So you lose some information. And so if we want to be a bit more precise, more formal, we could say that your full order, your real field, your high order, high fidelity solution is given by the linear approximation plus some correction term, say tau. This is also a field, so it's a function of space and possibly the parameters. And the tau is whatever, like you don't really know the specific form of your correction term, right? But what you know is that typically, if you increase the number of modes, so if you increase R, also the magnitude of the correction decreases. Now, why do we have two different curves here? Because ideally, you want your correction term to go to 0 as you increase the number of modes. But in practice, if you have, for instance, a convection-dominated flow, it turns out that you need very, 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 very many modes to get an acceptable error, right? And what we want to do in this work is basically find a way to reintroduce the contribution of this tau into the linear approximation, which is something that's meaningful every time you have to work with small data or you want to work with small data. So with small r. I also say that sometimes you have to work with small r because that's intrinsic to how you compute your projection to the linear space, because ultimately you do a singular value decomposition of your matrix of snapshots. So the maximum number of modes is actually equal to the number of snapshots you have to begin with, right? So if my data is made of 5 snapshots, I cannot hope to get more than 5 basis functions, right? And so sometimes you either have very few data to work with, or sometimes you just want a small model. And either way, you need to account for this correction term if you want to improve the accuracy of your solution, right? And so this brings us to the next section, which is what we have actually contributed to the methodology. And I want to start off by giving you a recipe to build our model. You might remember from the title, it's a very long title, but somewhere in there is the phrase quadratic closures, because what we did was precisely that. We wanted to close, quote unquote, close the linear approximation by introducing a correction term, which we assume is quadratic in the coefficients you already have. So instead of having the linear approximation, just the linear approximation, some AI, phi, we also add this tau term, which we assume as this shape. So it's basically the action of some quadratic operator, Cij, on the modes AI, Aj, that we already have from theory. And I just want to give you a recipe on how to build that, because it's really quite simple. It's really just one extra step with respect to doing standard POD. And all you need is just data and optionally a computer if you don't want to do that by hand. First things first, you need to perform POD. That's easy. That's already something very well understood. And once you've done your POD, basically you have this. You have this linear summation, right? You find the modes phi and the respective coefficients a. And then at this point, you can compute your exact correction. So this is the full order, the full order solution, which is data for you. So trust me, that's okay. This is data for you. So this is something you know, something you have. You simply compute the difference between what you have and the approximation through POD, right? And that's your exact correction. Then you make the ansatz. This correction has this specific quadratic form right here. What's left now, since we have A already, we just need to find the appropriate Cij such that this specific form matches the exact correction as close as possible. So just minimize the sum over all the snapshots you have of this difference, exact minus the specific form we want to give tau. And just a note, this is something that's already been done in the literature. This is something that has been studied. It turns out that this is like, doesn't turn out, maybe it's very clear to you, to me it wasn't very clear at the beginning, but this is really a linear least squares problem for the coefficients Cij, because it's quadratic in the coefficients A that you already have. So A is data and it's linear in these coefficients right here. So this linear least squares problem you can solve through traditional least squares solvers. And that's already been done, but sometimes it turns out that this is not satisfactory. Why? Because with linear least squares for certain classes of problems, you have the problem, sorry, that your solution to the optimization problem overfits data, for instance, or you need to regularize your problem for it to extrapolate, because of course, like the interesting thing here is not to build C and use that on data you already have. Like you want to get new coefficients for new values for your physical parameter and find new solutions. So you want this approximation to behave in a nice way for unseen values of mu, for instance, right? And also, that's not really an issue, but this is really just, there is a very strict correlation between the discretization of your problem and the shape of this operator, because remember, like you start with a domain, you discretize that, and you have, say, 1 million nodes in your domain. So your solution will have 1 million points. So your POD modes will have 1 million points. And this matrix right here is also going to carry that dimension. So it's technically, it could be a very large problem to solve. Right? So what we want to do, as we do in 2025 and 2026, we just do deep learning. So our approach is to approximate the operator C with a neural network. In fact, we tried two different architectures right here. We have the standard DiPoNet and the MIONet, multi-input operator network. The idea is the same. In both cases, you have your operator C as the output of a neural network. What changes is the input. So for the DiPoNet case, you have just coordinates X as input and the POD modes as input. The rationale here is that since you want to you want your quadratic operator to represent, quote unquote, the interactions between your POD modes. So it makes sense that you feed POD modes to the network in order for it to understand their intrinsic relationships and give you the best operator, right? And in fact, you can go a bit further in that, okay, for the multi-input operator network, we also feed the physical parameter mu to the model, making this effectively local in parameter space as well, because POD has the issue, which is not always an issue, but sometimes it's a limitation, that the modes do not depend on the parameter. So for each choice of your parameter, you have the same modes, which can be a limitation if your physics changes a lot. So for instance, if you want to consider a range of Reynolds number from 0 to 1 million, you have laminar and turbulent flow, and everything in between, your modes are fixed. So sometimes maybe you wouldn't need, if you have a laminar flow, you wouldn't need the turbulent modes to represent that, and vice versa, maybe, right? So in this case, we have an architecture that takes the physical parameter into account as well, and so possibly its locality in parameter space enhances the accuracy. And what's more, maybe it's not obvious from this diagram, is that this model is now continuous in space. So you're no longer, all it needs, it's just some coordinates. So you just give it some location in the domain, which need not be a discretized point in principle, right? And it will give you back the value of that quadratic operator in that location in space. This is very handy because, one, you kind of abstract yourself from the original problem discretization. Of course, you still rely on POD, so discretization is still important in here. It's not completely, say, mesh-free or mesh-less approach, right? But still, you can, for instance, evaluate your operator in new locations. But what's even more important is that you can leverage this continuity space to accelerate the training of your model, because instead of feeding it all the location in your domain, you just basically subsample your mesh. You find the best operator C on those mesh nodes, and then let the deep learning do the interpolation on the new nodes, because it can just feed the new coordinates. That's going to work. So these are the two models. We tested both, and I'm going to show you some results. But before doing that, let's go back to the original diagram. Hopefully now this makes more sense to you. This is basically the workflow, right? So you start with data. These are actual snapshots from a CFD simulations. You take those, you do proper orthogonal decomposition, you get the modes. Those are the actual first three modes that you get from this data, and you get the respective coefficients. Then, if you just want to do POD, you're good, because now you have all you need. You can build your base linear approximation like this. This is just, again, the linear combination of modes with the coefficients. But in our methodology, we go one step further. We take the modes, we feed those to a neural network together with coordinates and the physical parameter mu option, and then we get the quadratic operator C. As you can see here, like, those are the actual entries of the quadratic operator. As you can see, they are somewhat similar to the POD modes. You can actually think of those as some sort of modes as well. Those are, the explanation I give to myself is that, for instance, these field right here represent for each location in space the interaction of the first mode with itself. So as you can see, maybe it's more intense down here, right? And not very intense in the other regions as well. This is the same, but it's the interaction of the first and the second mode. Again, most intense down here and basically zero everywhere else, and so on and so forth, right? In this case, we have six entries for the quadratic operator, because we're building POD with three modes. So you have, in principle, 9 combinations of 3 modes with 3 modes, but it's symmetric because AB is, okay, commutativity of the product. But point is that once you have those, you combine these in such a way. So A, you take from here, you do this matrix vector product. It's just the action of the quadratic operator, and you get this correction term. As you can see, this is noticeably different from 0 from this case. And if you simply sum the two up, you get something that is hopefully closer to the real thing. You can kind of see, maybe from far away, no, not really, but you can kind of see that there is something strange down here in the linear approximation. With the correction, you correct that, and you're good to go. So the field is more accurate. So is that it? Actually, no. I want to show you some results. We tested these on 2 standard cases in fluid dynamics. The 2 flows we considered are this back step. So it's the flow over a backward facing step. Basically, you have this very long domain. Okay. You have your inlet here. You've got fluid coming in from here. The parameter in this case is the velocity of the fluid. Here it's in the range 180 meters per second. I think, I don't know, I don't even care about the unit, but point is that the flow is laminar, and depending on how fast the fluid is going, you're gonna have that it sticks more to this step or just doesn't care and goes forward, right? So everything here is still laminar, so there are no weird structures or anything. And the full order model in this case is just a finite element approximation. Don't even know if it's stabilized or whatever. But basically, there are roughly just 3,000 triangular elements and P2, P1 Taylor Root elements. So to be fair, we don't really consider all the degrees of freedom. So as you know, in P2 elements, you have 6 degrees of freedom, 4 degrees of freedom per element. 6 degrees of freedom per element. We just consider, I think, the cell centers instead of all the actual degrees of freedom. But still, if we were to consider all the degrees of freedom, probably the whole thing would have worked better because you just have more data to train on. Okay? And the other case is the lead-driven cavity flow. You have a moving top wall or some fluid moving here in the horizontal direction. Those walls are fixed. And you see that there is going to be recirculation in here, whatever. But the important thing here is that for the choice of viscosity, with these values of the top velocity, so in the range 0.5 to 1, we have very high Reynolds numbers. Now, this is a 2D simulation, so it's not really turbulence, but the point is that the flow in this case will be convection dominated. So POD, we expect POD to struggle way more in this case. So, and the full order model in this case, just a finite volume discretization. It's basically an open phone tutorial with 5,000 elements. Okay, just to give you a sense of the scale of the problems. These are not huge, of course. Like we have 3,000 elements, it's nothing for a real world application. 5,000 elements is nothing. But the great thing is that we are going to try to solve the same problems with just 3 to 9 POD modes. So order of 10 POD modes, which is a big reduction compared to 3 and 5,000, right? Now, we just want to show you some outputs, say. This is an example of field we want to match. This is for the backstep, and this is for the cavity. And then on the right panels, you can see the error coming from different models. So for instance, here we have standard POD. So this is the error that comes from the linear approximation of this flow. As you can see, you have issues down here. And fun fact, what you see here is kind of exactly the contribution of the higher order modes, like not higher order, like the subsequent modes, right? So in this case, I think we fixed 3 POD modes. And if you were to look at the fourth one, it would look something like this. And that's cool to see because, in fact, this error is just the difference between the full field, like the full solution, and the approximation we just removed. So what we hope to get is a correction that matches this so that everything is fine. And as you can see, the quadratic models, this is the one built from least squares, and this is the one from our neural network with the dependency on the parameter. In both cases, the error is much lower, as you can see, meaning that the quadratic correction is actually doing something. And what is most important, well, it's better for us because of the methodology, is that the error seems to be completely gone in this case with the neural network compared to the least squares, probably because the neural networks are generally better at extrapolating to new data, right? And also, I must say I'm cheating a little bit here because it's the same scale for all the 3 plots, so it's not exactly 0 here, of course. If I were to show you just this with its own color bar and everything, you wouldn't be all white, but point is that the scale is much lower, right? And the same goes for the cavity. As I told you, as I anticipated, this is a bit more problematic because it's convection dominated. So the linear approximation on its own is not enough. And if your linear approximation is too bad, you also, on the one hand, you would expect the quadratic contribution to be more important, right? But also keep in mind that the quadratic contribution is trained somehow on top of the linear approximation. So there's a bit of a balance there as well. If your linear approximation is just hopeless, then it's whatever, your quadratic correction might be very bad as well. But even in this case, even if it's not as good as the former one, we can see that the quadratic models are a bit better because you don't see this big error down here in the middle of the domain. And again, the neural network looks somewhat better than this. Not very clear in this case, I must say, but that's really interesting to see. And actually I have, so this is just for one snapshot. I have some results summarized in this box plot. This is for the back step. I have the same for the cavity. I'm going to show you in a while. And so let's focus a little bit on those four first four boxes here. So this is the error of the base model. So the error of POD. Error bars go to the maximum and minimum error. And then you have a comparison between the quadratic model built with least squares, the one built with the neural network without the dependence on the physical parameter, and the one with the dependence on physical parameter. So as you can see, the best model on average is the one based on the neural network with the dependence on the physical parameter, because it's, as I told you earlier, it's local in parameter space. So that's better. And so as you can see, like the maximum and minimum are not that far off when compared to the base model, but you're gonna have to trust me on this one. If you look at the variance of these two models, the variance of the the neural network model is typically much smaller than the variance of the least squares model, which means that the neural network is in general more robust and can extrapolate better. So it's more consistent, if you will, on new data, right? And I also want to show you something in this on the right here. As I mentioned earlier, since the neural network is continuous in space, you can also train the model on a subsample of the mesh. So, for instance, in this case, we tried to train the quadratic model, so the neural network, on just 10% of the mesh nodes, 20% of the mesh nodes, and 50%. And then just evaluate the errors and everything on the whole mesh. So see if we can not only extrapolate in the physical parameter, but also in physical space. And okay, you can kind of see that even with just 10% of data, the 10% of mesh nodes, the performance of the quadratic model is at least as good as the baseline model, which means that we are not adding anything bad to the original model, which is something good. And as you can see, if we go even, like we increase a little bit the size of the training dataset, by the point we use just 50% of the nodes. So for instance, find in the backstep case, you have 3,000 elements. So we use just 1,500 locations in the domain and extrapolate on the others. We get an error that it's even lower on average than the least squares model, which is quite good to me. And this means that you can speed up training quite significantly. I must say that training a least square model on this scale is still way cheaper than training a neural network because the backpropagation and everything. But if you go to meshes with, say, 1 million cells, maybe training the least squares model, it becomes a bit too expensive. And being able to subsample your domain to train a model that still performs good is quite important, in my opinion. And then this a bit involved, this heat map right here is just to show you that if we compare the quadratic model built with a neural network and the quadratic model built with least squares, or the quadratic model built with a neural network and the base model, you have an increase in accuracy that goes from 0%, basically, where you have too few training snapshots and too many POD modes. So for instance, in this case, if you have 10 training snapshots and 9 POD modes, you are almost saturating your POD energy. So when you compute the difference between the linear approximation of POD and the original snapshots, you have very, very little information left because you're almost using the maximum amount of data you can actually have, you have available, right? So this goes to say that the corrections in those cases are so small that neither the least squares model nor the neural network model can really learn anything from such little data, right? And so basically, this goes to say that the base model is the best you can do. The linear model is the best you can do. But if you start increasing the training set size, and even for a relatively large number of modes, you see that this is a percentage, basically. This means that, for instance, this right here shows you that the quadratic model built with the neural network is on average like 20% better than the baseline model and 8% better than the least squares model. And as you can see, you can go as up to 94% improvement in the accuracy with respect to the base model, and roughly 70% with respect to the least squares model. So it is way more accurate. It's just the same for the cavity. I think, well, these box plots are basically the same, not really worth mentioning. I want to show you that in this case, you actually have some combinations of parameters where the model built on neural networks is worse than either the original linear model or even the quadratic model. So, for instance, in these cases right here, you see that this is worse than the baseline model. And in fact, this is something we expect because it's a difficult problem. So it's convection dominated. You have few data and relatively many modes. So the corrections you are trying to learn are very difficult to learn. The training is very sensitive to the choice of hyperparameters, so learning rates and all this kind of even optimizers, I think. So even in the best case scenario, maybe you could go as before, you could reach the same accuracy as the baseline linear model, but in general, like in this case, we got something that was actually worse. That's clearly not advisable, but still. But even in this case, you see like the neural network is worse than the base case, but it is still 60% better than the least squares model, meaning that given that neither least squares nor the neural network are learning anything meaningful, at least the neural network is less wrong than the least squares model, right? And for instance, in this case, the least squares is just better than the neural network, and we have to live with that, but okay. So just summarize, this is what we have learned from this work. We have compared an existing methodology to build quadratic corrections to reduce to linear POD-based ROMs. And what we have observed in general is that this least squares method is more accurate than linear POD, but the neural networks are, again, in general, more accurate than the least squares. And we have these key differences in that least squares is discrete in space, while the neural network is continuous in space. So it's independent of the mesh size. So the size of your optimization problem typically doesn't grow with your mesh. And again, you can do that subsampling thing to speed up the training. And you have the least squares model is generally global in parameter space. You probably can build a local model in parameter space as well for the least squares, but it's not so trivial, I don't think. And whereas neural networks can be local in parameter space, and we've seen that the accuracy greatly improves. And then this is just something that's still to be verified, because neural networks are supposedly more regular, like they have a larger implicit regularization, which makes them more suitable to extrapolation to new data and whatnot. Whereas least squares, you have to regularize, say, by hand, which it's a bit of an art in itself. Right? Up next, I must be honest, I'm not really doing that right now, and I'll do something else. But it would be interesting to see what we can do with different architectures, say convolutional networks, graph networks, whatever. The most important thing would be to make the methodology more robust. So as you can see, as you've seen sometimes, the neural networks are worse than the base model. That's not advisable. So we want to make that at least as good as the baseline model always. And then extend to time-dependent problems is absolutely non-trivial. I've tried that. It went very poorly, so it's not in the presentation, but that's something that would be interesting to explore in the future. And I think that, yeah, that's it. You can check out still a preprint. It's going to be out on a journal soon, hopefully. So yeah, that's it. If you have questions, please do ask.
Thank you for your interesting talk. It was interesting. Are there any question? Otherwise, maybe. Yes, please.
Thank you, Gabriele. Very, very nice too. Interesting. I have just a curiosity. Tau is still orthogonal when you build your synthetic C, or I mean, if I apply POD on a reconstruction of by means of POD modes, the POD results are the same.
The POD is just a POD. Your tau is something you just literally
orthogonal to the mode.
It should be orthogonal to the mode. Like yes, it should lie outside of the POD space.
So you don't enforce in the cost function of your.
I think it's been a while. I think we tried both things. We tried.
I mean, in the interpolation regime, you have that tau is still orthogonal or not?
I think it should be, like, in principle, it should be orthogonal to the POD modes. Like each entry, you can actually prove that pen and paper that it's all the entries should be orthogonal. You can try to enforce that weakly in your loss function, but as it turns out, the optimization just goes there quite often. So if you look at, say, the inner product with each POD mode and each entry of the quadratic operator, they're kind of orthogonal. And we didn't really see any benefit in enforcing the constraint explicitly in the loss. It's just something you have to compute. It's just extra work, not really beneficial. But in general, it will kind of be orthogonal.
And what happens if you put that ansatz into equations, like for general?
Yeah, well,
because if you have still orthogonality, you can play something in the product.
But in your equations, so this is fully data driven, so we do interpolation actually.
No, I mean you said from non-intrusive to
intrusive. This would be a good question for Anna, I think. I think she did work on that intrusively. But I don't know, actually. Like, you probably, I think that some of the original works where they do least squares, they are intrusive ROMs, and you do exploit this somewhere at some point. Here, it wasn't really, at least it didn't occur to me that we could exploit that information other than forcing the coefficients of the quadratic operator to be non-redundant. Like, you don't want to learn other representation of the same POD mode. But we observed that this generally doesn't happen. So I don't know if this answers your question, maybe not. But point is, I didn't see any reason why we would want to enforce this extra constraint on tau, for instance. And I don't really see an obvious way you could exploit that for this kind of problem because of the interpolation and everything. Going intrusive, didn't really consider that, to be honest.
This is actually a follow-up on this, but it's like really ask you already, like it's you are already trying to optimize only one side of the quadratic operator, right?
Yes,
it's exactly. You report strongly in this case to be symmetric.
In fact, yes, exactly. Like you see, I just laid them out as a matrix, but it's really just a vector.
Yeah.
It's
like in the same way that you learn automatically to be orthogonal, probably people that maybe you learn automatically to be symmetric as well. If you try to optimize everything, it will just tell you that matter.
Yeah, maybe in the very early stages of this work, maybe I did try to learn the whole thing. Actually, yes. In fact, yes. Matter of fact, I think I did try to learn the whole thing at the beginning, and I think, don't quote me on this, but maybe I think it also learns something that is symmetric as well, because then you combine it's the somewhat intrinsic in the way you combine it in the loss function, right? Because you just do a product, and if you swap, then
Yeah, you're having five things.
exactly. So maybe the magnitude is just halved because because of, but it's the shape, let's say the qualitative shape is the same. Yeah.
Any other question? Otherwise, I have one philosophical
Yes.
and one curiosity. Let's start with philosophical.
As you wish. Yeah.
No, it's better the other.
Okay.
Philosophical. We can discuss later.
Okay.
Okay, one curiosity. Why it is quadratic?
Just for convenience, you could in principle go further in the degree of polynomial. I think there are works where they actually show like that the mathematics still holds if you go up higher degree.
Okay, if you do an expansion with the modes of
You could do you could do quadratic and then add a cubic term and so on and so forth.
and the results improve, or
In principle, I think so. In practice, I don't really know, because sometimes even in these cases, maybe for different classes of problems, maybe yes. In these cases, the corrections were already so small and so so small that sometimes even with just the quadratic model, you struggle to capturing them. So that's even a matter of training. And sometimes like the error just drops so small that, because I imagine if you want to add a cubic term, you do the same thing. You do the quadratic expansion, subtract, find the cubic correction, and so on. But if your error is order 10 to the minus 4 or something, then you need to learn something that's order of 10 to the minus 4, and that's trickier to do.
yes, of course. So just for convenience.
Yes. Yes.
Okay, now the philosophical. Yes. Can you go to slide 14?
Yes. I'm sorry for the. Oh, yes.
What do you mean by laminar?
I mean low Reynolds. No,
How
you know it's 2D. Reynolds is based on, I think it's based on the bulk velocity. The integral of the thing, right? And the width of that. So that's fixed. You just change the parameter is okay. The inlet profile is parabolic. What you change is the maximum of the parabolic profile. So the amplitude, basically. So as you increase, you have more volumetric things. So you increase Reynolds based on that. It's not really important. We never work with Reynolds actually. This is all just the dimensional form of the equations. And that's just to say that if you were to compute the Reynolds number for these cases, it would be low, order of 100. Not even, order of 100.
And below is the ortholaminar or the cavity?
No, it's 2D.
Where is
More than
It's actually
by definition, it's not necessarily steady.
this is the full order. The full order models are not steady solutions. So they are transient, and at some point it stabilizes and you take the last one.
And you use have you used ecoform?
I didn't do those myself. I know. No, that's okay. That has reached the steady state, so there is no time involved here. But also it's 2D. There is no turbulence model in any direction. There's no homogeneity. Just plain 2D simulation. It's 3D because it's open form, but you don't solve in any other direction, and you don't compile.
Because you're essential.
So point here is that if you have small velocities, you have like this kind of these kind of structures you don't really see. It's more regular, say, for lower velocities, here you have bigger vortex or recirculation zone. You have the structures here in the corners. I think so. That's the issue.
Okay. Another that it is just personal. How have you done your scheme of the neural network? Which program have you used?
It's Draw.io, I think it's called.
Draw.io.
Yeah, it's an online. Thing.
Online.
Yeah.
Okay, good. Think about it.
Yeah. Okay.
That's one question. When you compare, for example, without the correction and with the correction,
Yes.
are you taking the same number of modes?
Yes.
Because like when you have the correction, I think you have like the extra quadratic modes.
Yeah. Okay. So yes, that's a good point. You take the same number of POD modes. So this is 3 POD modes, and for example, this one is just the POD mode, and here you also have the quadratic term. So you have the 3 POD mode and the quadratic term on top.
Yeah.
So that's you could see as having more modes, but those are not technically not POD modes. They are the quadratic coefficients.
Yeah.
Maybe just a curiosity. So you said about the possibility to extend to a cubic term.
Yes.
But I think that like for dimensional reasons, it could be.
It would be okay
because it scales
exactly
exponentially.
for the issue is that if you want to do that with least squares, you have a big whole matrix like tensors sorts. If you do the neural network, it's easier because you get rid of the space dimension of your tensor. So you still have technically a 3-dimensional output, would no longer be a matrix but a tensor, but you just travel that.
You could do it, but not comparing it to the squares.
Of course, like if you want to use 3 POD modes and do a cubic term, still kind of tractable. 5 modes, like 9 modes, and the cubic term. That's at that point it has to be full of.
One last thing, maybe about what Antonio said before. When you apply the correction term, I'm not sure about the orthogonality, but what I imagine is that when you apply the correction and then you project again that new solution you do not have the same one you had initially. Like if you project
the projection of the structure.
I think that it is not invariant under the projection because
in that sense.
Because you're in some sense changing the shape of the manifold where the solution is running. So
actually, yes.
Maybe it's not linear anymore, and so the projection is not invariant.
But if the correction actually lives on the orthogonal component, I think it should, in theory, it should live outside of your POD space. So if you redo that and project, I think so maybe I'm just no. I don't know. Maybe
because I imagine that supposing it to be quadratic, it may create a different shape, and so be on the exact orthogonal direction. But I'm not sure about this. I should.
Maybe.
But
That's a good question.
I think that it could be projected to another vector in the space. Yes. Maybe near it.
Might be.
Some,
Might be, yes. Indeed.
Any other question?
now or never.
Also from online. If there are, then thanks again, Gabriele.